Welcome to lecture 4A. This is an extension of lecture 3rd and 4th, and the topic of this present lecture is a wear phenomena defined by dimensionless parameters. We have covered two wear mechanism, which is a two significant wear mechanism, adhesion and abrasion, in last two lectures. And we understood the adhesion occurs when two surfaces come in close contact and experience bonding force. This causes the removal or transfer of the material from one surface to another, and finally leading to the generation of wear debris and material loss. We know that adhesive wear is more common in metal to metal contacts. Abrasive wear occurs when hard particle or asperity of one surface come into the closer contact of the soft surface. This asperity flow through the material, cut the softer surface, leading the generation of wear debris and material loss. And there are many factors which affect the abrasive wear, like a size, shape, concentration of abrasive particles, how much of, stress has been applied, what is the relative motion, and what kind of sliding to the rolling ratio is present there. So, what we can say, adhesion and abrasion can happen independently or simultaneously in real world situation. Like if there is an abrasive particle and it has some sort of a more bonding force towards a material, it will cause adhesive wear also. And once adhesive wear makes a particle, or maybe say the wear debris, that can cause a abrasive wear. So, this kind of wear mechanism can happen simultaneously also. If you remember, we covered adhesion wear and abrasive wear, and I am trying to highlight the few features of the few slides, obviously the few diagrams which we have already covered. In adhesive wear, we say that major thing is a bonding force between the two asperities, two surfaces, and because of the bonding force, what will happen, there will be a plastic zone, or what we call a micro weld operation will happen. And if you apply a relative motion on the one of the surface, then there is a possibility that material will get transferred or get detached from a softer surface. It can attach to the harder surface, or there is a transfer, or we can say the material is removed, but finally it will lead to the wear debris. And this kind of Orchard equation was developed for the adhesive wear. We say that Orchard equation or Orchard wear equation is basically qualitative in nature, because there are many variables, and if you repeat the number of experiments at different situation, even in the same load, same I would say that sliding distance, same hardness, we may get a different results. So, that is why we bring some sort of statistical parameter, that is what we use a word is, this is a wear coefficient. So, this K1 is a kind of statistical in nature, it will vary, and then it should be always lesser than 1. That is a probability that wear will be, and the particle will be removed due to the wear, and then it should not be more than 1. So, this is what we have learned in adhesive wear. Coming to the abrasive wear, we say it can be two asperity contact, or it can be a three body abrasion also, both the possibilities are there, and Rabinowicz's equation was derived in this lecture. Also in this case, what we understood, the wear volume can be calculated by this equation. There is again W, there is applied load, L is a sliding distance, H is a hardness of the softer surface. So, again this K is a probabilistic factor, or is a probability of the wear debris generation, and then we can relate these both the probabilities, the K1 and the K, with a wear curve. What we have already covered is the bottom curve, something like A to B, there is a rapid wear, or we say that the acceleration, the rate of the wear is very high in A to B zone, and similarly there will be a rapid wear in a C to D also. While B to C wear will be more or less constant, maybe gradually increasing. So, naturally when we talk about the constant K or K1, mostly it should be related to BC, then only we will be getting a repeatable results. Otherwise, we will not be able to get repeatable results. What are the reason for that? Because even in initial, we know that surface will have asperities, and initial surface will have a very sharp asperities. What is the meaning of sharp asperities? Is like alpha, this angle will be very small. That means spikiness or maybe the peakness will be very high, and that is why we say that during the running in time, this alpha will increase. Quite possible this surface will get a slightly curvature at the bottom, and this angle may turn out to be like 150 degree, 160 degree, while initially it can be 20 degree, 30 degree, 40 degree also. While this alpha in this case overall 2 alpha will be 2 alpha will be equal to the 150-60 degree, because alpha is a 50% of the cone angle, and then it will be naturally, if I say alpha in this case, then it will turn out to be 75 to 80 degree. It will not be in the degree in this case, and that's what we have learned in lecture 3 and lecture 4. And just to repeat the same thing, what we say that the k is a probability and the k1 is a probability equal to 1, where every junction involved in the process of addition or abrasion, then the wear fragment is coming, that means 100% failure is happening. While k or k1 equal to 0.1, the 1/10 of the junction which are in contact will be generating the wear debris. While coming to the k is equal to or k1 equal to the 10⁻⁻7, that means only 1 in 10 million contacts, or maybe the repetitive contact whatever happens, it will generate only one wear fragment. This is a more like advisable if the wear factor in this case is 10⁻⁻7 or even lesser. That is what our aim, or we should make a product such a manner that it can sustain that much life. And sometime, because this is a very closely related to the fatigue process, that is why we say this is a micro fatigue process. So, this is what we have learned, and then we know that wear coefficient plays important role. That is why we are giving a number now. We are talking about a dimensionless parameters. As I say, in reality there will be many parameters. We cannot quantify, we cannot consider all the parameters. So, that is why we required some different way to look at the problem, and that is why we consider dimensionless parameters. Just to explain what I have mentioned, I am considering one example here. This is the example would say that a hard steel surface considering an array of conical asperities. Now, conical asperities, when we say, we need to look at the surfaces also. Naturally, this cone angle will be different than this cone angle than this cone angle. Actually, what Ravnowicz did, it was more like a generation with a single asperity, but in reality it is a multi asperities. So, variability will be there. Again, we are considering only probabilistic. So, and it is statistical, that is why we need to perform number of experiment to come up with the right results. Maybe in one experiment we get a one kind of one set of the results, other experiment we may get a different results, because it is statistical in nature. So, that is why we are trying to consider this example to understand what is really happening. So, what we say is the array of the conical asperities, but again we are assuming that average cone angle is a 120 degree. This is just an assumption, so that we can do some sort of theoretical formulation, or we can understand mechanics, or we can say we try to predict something which may not be 100% correct, but it will give us some sort of what we say the concept, and then we can compare different materials. So, that is why the dimensionless numbers are required when we want to compare. They are not absolute. We can't say this material is the best. Yeah, if there are 4 materials, we can say among these 4 materials, this material is the best. That is a one. We can't say absolutely this material is the best in all the situation. No, it is not possible. So, whatever the situation we experiment or we come up with the results, that will be the better. But again, we really require some sort of understanding, some sort of knowledge. Otherwise, number of experiments which we need to conduct will be many. But when we have a knowledge and we have understanding, number of experiments will reduce, and it will give really conclusive good results. So, this is what we are saying, average cone angle is a 120 degree, and the load has been given. However, in the load of 15 Newton, we are not going to consider this load, reason being we already have a cone angle, and then when we say Rabinovics, wear coefficient can be figured out by cone angle itself. However, in reality we will not have a cone angle, we will require some other parameters like a load, we will have require a sliding speed, how much wear is volume is happening, how much, what is the hardness, those parameters will be required. In addition, temperature, vibration, many things will be required. So, let us for this example, to keep it simple, we are saying that calculate the wear coefficient and show how this coefficient k keeps changing when the asperity angle or we say 2 alpha or the cone angle is varying between the 60 to 180 degrees. So, this is one of the numerical to understand what is really happening. So, if I try to summarize what are the given data, conical angle is given a 120 degree. So, half angle or alpha will be given a theta by 2 will be 60 degree. Applied load as I say for this because we say we have a alpha available, where coefficient will not really require to consider the load. The cone angle is sufficient, reason being abrasive wear coefficient is given generally like this, the coefficient k is given by 2 pi 10 alpha. So, if alpha has been given to me, I will not consider the load. However, as in an example that these data are given, we are considering. Now, if we want to really do a simulation, if we want to really do a numerical, some sort of analysis, we require some sort of a software, and I am happy to inform that the MathWork company has agreed to give a free software of the MATLAB to all the students, and then they will upload also the various tutorials. So, that every student can learn the MATLAB, they do exercise, and based on that we can give some sort of exercise to them. So, this is the first I have given, this is the we have written very simple MATLAB code. What has been given as such, given data, what has been mentioned, we are giving theta in this case, because we say here it is a 120 degree, but when we are transferring and an addition has been asked that you figure out what will be the angle from what will be the k value when angle is varying from 60 to 180 degree. So, the MATLAB gives a very good result immediately, where we can say theta, it is a varying from 60, that is the initial value, final value is a 180 degree, and increment is a 1, that means initially it will take a 60 degree, then 61, then 62, then 63, then 64. So, it will vary that way, and then we do not have to, we can do a mathematical calculation, simple calculator, but that will take long with a huge time. I may say that it will be unnecessary too much work for us. So, that is why the code is better, it gives a few other fraction of second all the results. That is why we are saying this angle of conical asperities in the degree has been mentioned. That alpha we are interested, that will be theta by 2, actually it will be whatever the number, it will be divided by 2. Apply load, as again I am using the word, it is not required for the calculation. Now, once alpha is known, I can write the k value in terms of alpha. Here the formula is already given, 2 divided by pi, pi has been given, this is already a symbol available in the MATLAB, we can write directly pi, we do not have to write down 3.145 something, we do not have to write that, just write a pi, that is more than sufficient. As a 10 is generally expressed in terms of the radian. So, that is why we are writing the 10 degree to radian, that whatever I am giving in information alpha in terms of the degree, and then for calculation purpose we should convert to the radians, and that has been mentioned over here. So, this will give you the value of the k. In one shot we will get a value of k, and I say increment maybe the starting value 61, final value 180, and increment of in each value will be 111. So, 160, then 61, then 62, then 63, it will be continuously done. Then what we are trying to figure out, as we are calculating at the 50 degree or 60 degree, then what will happen the 180 degree. So, this is a very clearly as mentioned over here, the wear coefficient is continuously decreasing with the increase of the asperity angle, and that is what we understood also. Abrasiveness of asperity will decrease if the cone angle is going to increase, because there will be round edge at the bottom, it will not be very sharp, it can plow, but it cannot cut. it will reduce the wear rate. So, that is important for us, and then maybe at around 60 degree it will turn out to be 1, it can be lesser, and again is there is a probability is a number. We want a qualitative comparison, we are not seeing absolute comparison for us. So, this is what we are mentioning, and 120 degree absolute value we can find out 0.368 is the value of this constant. And based on this we can say in reality we need to think about a multi-aspirative model, not a single aspirative model which has been given by this relation. So, when we compare we do not have to worry single aspirative, multi-aspirative, we had to say what is the value of k, and if the value of k is a lower, that is a better. When we compare, when we design, we say we lower the value, the better the results. So, we can say reason being why we have been counting this kind of equation, because I have not observed any equation which is a generalized equation to predict the wear. There may be more than 2000 equation in literature, but not a single equation is foolproof, gives a complete answer. So, that is why we want to go back to the old equations, and we say that we need to perform experiment to come up with the right results. Reason being that every experiment will have some sort of difference, maybe some different lubricant, humidity, temperature, rigidity and all. So, we really require some sort of experiments to do, that is why we are emphasizing on this non-dimensional number. That is why we say that for comparison purpose, dimensionless wear coefficient can be utilized, and maybe in my view it should be utilized. How do we compare? How do we say which is the good, which is the bad? You say that for unacceptable, that means if the wear rate is more than 0.001, the wear coefficient is more than 0.001, that is completely unacceptable. We should reject all the solutions, whatever is coming out. However, if the thinking over the micro fatigue, and then wear coefficient is lesser than 10⁻⁷, yeah, we can think the system is really doing work, and then we need to work on that to improve, maybe say to further reduce the value k. Maybe if 10⁻⁴, 10⁻⁵, -15, 10⁻�XVI, that is we are going with the ultra mild wear domain. As I mentioned, when the two particles and the two solid surfaces come in a contact, you cannot avoid the wear. Wear is a necessary evil, will happen. How can you minimize? That is engineering, that is a science, and we should work on that. Now, just to elaborate whatever I mentioned, I am giving in a slide form. We say the comparative analysis of the wear phenomena using dimensionless parameter. However, we can write the parameters also. I am giving only one parameter, stress, reason being coefficient of friction is known to you, that is another non-dimensional number, and for the reality we require both coefficient k as well as the mu, coefficient of friction as well as the wear coefficient, both are required for the completeness. However, the coefficient of friction has been explained in a number of other courses in more detail. So, I am not giving much emphasis on that, I am just concentrating only the non-dimensional wear coefficient. So, just to elaborate what I mentioned is a dimensionless matrix are frequently employed to describe and analyze the wear phenomena. Now, it really gives helps to the engineers and scientists to examine different factors including load. I want to increase the load, what will happen, increase the sliding distance, what will happen, maybe the material characterization, it may be thermal aspects, maybe the density, maybe the porosity will be really affecting the wear phenomena, and we can compare it very different manners. And then it is another one is the contact condition, even there is some sort of what we say contamination layer. Sometimes contaminated layer really helps a lot, it reduces the wear significantly, and sometimes contamination layer increases the wear significantly. So, we really require some parameters to compare, that is why we are proposing this dimensionless wear parameter should be accounted. Now, I say there are maybe a number of other parameters. What are the other parameters? Many times you can find out the systems are not performing well, reason being the system to system rigidity changes. That is why the vibration phenomena will come into picture, that will change a contact. Sometimes the contact has a more load on the top of that, sometimes less. So, we will get a frictional also variation in that, friction coefficient will not be constant, it will become a statistical in a big way. Even the test environment may change, as I said, the pollution, maybe gases, we will be considering that kind of environmental effect on wear phenomena or the corrosion phenomena or on surface degradation, and then the one complete lecture on that, what is the really effect of environment. Now, coming to that and the wear phenomena, we say every wear process entails many variables. As far as my knowledge is concerned, even the adhesive wear, if I go with a micro model kind of thing, we say, oh, there are 25 variables, how will I account those? And there are so many variables, and then many variables cannot be measured also. We know these are the variables, how do I measure? So, that is why we say the wear phenomenon itself is a statistical, and wear coefficient is a statistical. So, why not we account wear coefficient? If we are getting repeatable results, we rely on that. And again we say that it is not absolute value, it is just for the comparison purpose. So, it gives a qualitative comparison or maybe among some materials or some lubricants, that is why we are using this kind of non-dimensional number. As I mentioned that friction coefficient is another non-dimensional number which you have already studied, and maybe it has been elaborated in number of courses. So, this is basically a ratio of the frictional force to the normal force acting on the surfaces. Now, because the friction force controls the degree of interaction, if interaction is a lesser, metal to metal contact is a lesser, we know the coefficient of friction will come down significantly, and it causes the energy loss, that means like a temperature rise also will occur if there is a coefficient of friction on higher side, and if the temperature changes, naturally material property to some extent will change, and that will cause a wear difference, maybe a different kind of wear. So, that is why we say this also will affect the wear phenomena. So, that is why we say the dimensionless, this parameter is dimensionless, and this is a kind of a critical factor to controlling the wear. Again, it is a critical factor, but there is no direct relation. Coefficient of friction cannot be directly related to wear. I can't say that, oh, high coefficient of friction means high wear, low coefficient of friction means low wear. No, there is a relation, there is a critical factor, but there is no direct relation. It will vary, it depends on the situation. Now, coming to the wear coefficient, we say it is again a dimensionless, and it explains the kind of the wear rate, means if the coefficient is very high, naturally the rate of the wear will be phenomenal, very high, and we can't accept that, and we need to really change the design, we need to change the material, we need to change the temperature conditions, or maybe we need to bring some sort of coating, or maybe we want to bring some sort of a lubricant also. So, that is what we to control it. Now, it connects a sliding distance, that is what we have covered in adhesive wear and abrasive wear. It depends also on the normal load, it depends on the material characterization, particularly we consider the hardness, but toughness is one of the major thing. The toughness also plays an important role to the wear volume in this case. Sometime instead of the normal load, people think about the contact pressure, they say that is more realistic. Load does not give the kind of thing. So, sometimes people use a contact pressure, sometimes they use a Hertzian stress. So, these are the depending on the different kind of mechanism when we are trying to explain. So, sometimes we use a normal load, sometimes a contact pressure, sometimes Hertzian stress, but when we do experiment, it is a dimensionless wear coefficient, that makes more sense to us. Now, why we are explaining so many things? Reason being, nothing is absolute. I am just citing a few examples from the literature from AS on the handbook. That is why I say that in this case they have given auto engine camshaft, they have given example of the camshaft. They do not go ahead with through hardening, the complete hardening procedure. What is the reason? Because once they do for this kind of thing, there is a possibility of cracking, or maybe the toughness will come down and wear rate will increase. So, one hand wear equation say increase the hardness, it will give better results, while you say do not go to beyond certain hardness, where the compromise happens on the kind of toughness, that becomes a brittle instead of ductile material. So, we should have a upper limit on hardness, that is what we are trying to communicate, and that happens when we try to do experiment, we find out the wear rate, and then the wear coefficient, we know this hardness is giving some wear coefficient, increasing hardness is increasing the wear coefficient, means something is wrong, some other mechanism is going to play a major role compared to what was existing, then the mechanism was playing a role there. Now, we see another one, the some brake material wear out much faster at the low speed. So, again the low speed and high speed, generally we say that increasing speed is going to increase the sliding distance. When increasing the sliding distance, wear should increase, but no, it does not happen always. Some wear in the brake material having different kind of configuration, different type of the grain structure, they wear more at the low speed. So, actually there will be some different mechanism and we need to understand. So, finding the K value really give us some sort of input to brainstorm the solution, why it is happening. So, that we become more aware something is changing, maybe whatever the assumption about the mechanism what we thought may not be correct and we need to really change. So, it is basically this coefficient really helps us to brainstorm, to deliberate, to understand what is the new thing coming out, and then we need to really work on that. So, another example we say that the hardenable steel wear out more quickly, the sliding speed coming, this is what we mentioned already here. And then another one is that if you are really thinking about a wear, do not rely on only on literature. We need to do some sort of simulative testing. What is the meaning of simulative testing? I required some real experiment on the ball bearing, and there is a load, there is a rotational speed, and why I want to perform small experiment only on one ball and a race, not a multi ball rolls, and maybe without the presence of lubricant or with the absence of the lubricant, then I need to do simulation. Now, what is the really simulated condition? Once I drive the simulated condition, then I should perform experiments on that. That will give me the right results. This is what we are trying to convey, that dimensionless parameters are really playing an important role, and we should work on that and come up with the right results. Now, whatever I mentioned, I am trying to write on the slide and this whatever I and try to brief on the slide. We say the wear coefficient. Now, wear behavior is influenced by the numerous factors, that is what I mentioned, including material properties, surface condition. Even you change the surface roughness, wear coefficient will change significantly. Now, change the lubricant, not only lubricant or lubrication, lubricant type also, it will change significantly. Temperature, contact geometry. So, more and more knowledge will always help to really get a solution. Sometimes people feel, oh, there are so many numerous and so many parameters, why shall I worry? I will perform an experiment, that will be more than sufficient. No, even performing experiment will not give a reliable result unless we have all understanding about the system, and then that comes only by understanding going through the literature, understanding the literature, and then coming with own the setup which will give the right results. So, that is what we are trying to understand. So, we say that therefore, the knowledge of wear coefficient in connection to the specific wear phenomena is a crucial particularly for proper wear comparison and analysis. So, wear coefficient is very essential when we want to compare different material, different lubricant, maybe different situation, different temperature, different hardnesses. So, we need to really require. So, when we are comparing two different phenomena of the wear such as adhesive wear and abrasive wear, it is possible to express them in dimensionless form, and that is why we say that for comparison purpose, for evaluation purpose of the different materials, or to understand the severity of the wear in different system, wear coefficient will be very important. So, I have written 4 bullet points. What do we say? The first, wear coefficient quantify and compare the severity of abrasive and adhesive wear. We are just writing here the two wear mechanism, but in the future lectures we will be covering more and more type of the wear mechanism. We can compare wear coefficient for that also. The knowledge of wear coefficient add in selecting appropriate material. When I want to select the material, which material will be the better material, I can use the wear coefficient values. Even which coating will be better coating, I should choose the wear coefficient related to the wear, those kind of coatings. Similarly, for lubricant, surface treatment. So, whatever the treatment or surface treatment which we will be doing in the future, again we will bring this wear coefficient to the knowledge of wear coefficient will really help us to choose the right coating, right material, right lubricant, right surface treatment. Another one main feature has been saying, even in the case of the maintenance, we can choose whether after 1 week maintenance is required, after 10 days maintenance is required, after 365 days maintenance is required, because wear coefficient very low, doesn't require frequent maintenance, and ideally we should not really maintain any system. For that purpose we require very low wear rate with something like ultra mild wear, 10 is to minus 19, 10 is to minus 20, something like that. And moreover, we also say the product reliability, if the wear coefficient is very low, product reliability will further increase in the sense, and it will also reduce the downtime. So, it will be the cost economic. That is why we really require a wear coefficient. And another one, as I mentioned already, that it provides some sort of relative severity and material loss impacts. So, this is what I am trying to write, that these are the many advantages of wear coefficient. Let us take a 3-4 example which comes obviously in a mind related to the wear coefficient. What is the first question? Maybe say question number 1 comes, how can experimental data from pin on disc tribometer, we will be discussing different kind of tribometer in the future lectures. So, that will come into the here, another we are just considering only pin on disc, but there are many tribometers, and there is another one setup which we call a 4-ball tester. So, there are two things, so one is the pin on disc tribometer and 4-ball tester. We can perform experiment, we can find out the wear coefficient by performing experiments. So, what we are asking, how can experimental data from pin on disc tribometer and a 4-ball tester be used to compare performance of lubricant or materials? I am writing both. It can be used for the material comparison, but if you are using same material but different lubricant, it can be used for the different lubricant also. So, this is the question 1, and what we can write here, that by using dimensional wear coefficient, we have a simple thumb rule, the lesser the better. If the coefficient value is very low, that will naturally material will be better or lubricant will be better, and moreover it can be in a kind of standardized, and then it gives a comparison or qualitative or quantitative comparison, depends on how accurately we are performing experiment or what kind of a setup we are using. If you are using very sophisticated equipment, then maybe possibility quantitative comparison can come at the nano level or macro level, but at the macro level it may be again qualitative comparison. So, by doing this we can rank the materials like material 1, 2, 3, 4, and then something like we evaluate the various lubricant also, and based on the what is the performance and how efficient those materials or lubricants are there. So, this really helps us. Now, second question which comes in the mind is that what is the significance of the comparing wear results using wear coefficient? That is an obvious question. We say when comparing the wear results using wear coefficient, influence of the specific test setting is eliminated. Reason being, the material is being tested, and then we are comparing. Sometime we want to compare only material, then we can figure out, but even that slightly different condition, maybe time in the one place to other place, it may affect to some extent, but it will affect all materials or maybe in almost whatever we are using in the same way. So, it will really give us some sort of good comparison and remove the influence of a specific test setting in this case. It can be say that it is the standardized comparison across the test conditions or test techniques or the setups. So, it really helps, otherwise we will be stick to the test setup, and one setup will give one result, something like a pin on disc will give one set of results, the 4-ball tester will give another set of the results, and then we will be unnecessarily worried why the coefficient of friction or maybe say this wear coefficient is very low in 4-ball tester and very high in a pin on disc, because that will give us some sort of test setting that happens because of test settings. Now, if there are severe comparing same materials, same lubricant, that material will give a similar kind of results. If there is some variation, then it gives really thinking why it is happening. Is it because of surface roughness? Is it because of the test sample which we have made is different? So, that is what it really gives some sort of thinking, and then we can really go in a design philosophy, and then we can really rectify whatever the faults were happening. So, third question comes something, what are the benefits of using the wear coefficient in assessing the lubricant and material performance? I had to some extent I already explained, but again I am trying to write down here. Wear coefficient gives the numerical values, is basically numbers, and engineers means numbers. So, engineering it gives us some numbers, and that will give us some sort of comparison. Again I am using the word quantitative comparison, but it is a relative comparison, it is not absolute. Do not go with the absolute values, yeah this is means this will be always there. Now, in one setup they are giving the results, again we are 4 material, 5 material, 10 material, 100 material, we can compare, but you change the setup, it may give small kind of a difference in the result, maybe the ranking is same, but absolute value may change. So, that is why we say that we will go with the relative value, we will go the ranking, and then we can choose a best material, we can choose a best lubricant from that point of view. So, from evaluation point of view, ranking point of view, these are the good results, it can provide a good results, and many times it gives a repeatability, even though I am using the word is a statistical. So, we use a bar diagram or the bar chart kind of thing, or maybe we give some sort of range, it varies coefficient of friction or the wear coefficient between this to this, but it will be kind of repeatable. And then because these are statistical, naturally it will not give exactly dot same results, it will have variation, but it will be repeatable. That means, whatever the range comes, results will be repeated in that range itself. So, it gives some sort of it allows to optimize the surface. When we select the coating, it will come again that we will choose a coating which really gives the best performance, we will choose a lubricant which gives the best performance, and then so that is why the best performance means optimization. And another one is that is a really uniform or standardized method to compare the all lubricant and materials. So, in my view, wear coefficient should be utilized. You have already learned the coefficient of friction. In future, we will be comparing both together, but wear coefficient is a new concept compared to the coefficient of friction, which is very popular among all the streams. Wear coefficient is not that much popular. So, we are trying to propose in this. We will be covering in future number of examples, will be bringing the wear coefficient comparison, and will try to demonstrate how to rank the material, how to rank the coating, how to rank the lubricant in that. Thank you for your attention.